Reporting for Fun Robotics Network, I'm Yashis, and with me on Behind the Bot is Team 11329 ICE Robotics from Indiana. They came here to the West Lafayette Qualifying Tournament 2 with an incredible robot, and they finished as the winning Alliance captain. Learn more about their incredible robot with an amazing Level 3 hang on Behind the Bot. To start things off, let's talk about how you guys planned the beginning of the season when the game first released, as this game was a little more complex than other seasons like Power Play or Center Stage.
Every single year, we start off by analyzing at kickoff, we see all the different ways that we can score points and how we want to do them. And we spend all of our time brainstorming different ideas, designs, and then we go and rapidly prototype them through 3D printed models. For example, this intake that we have on our robot has gone through 12 different iterations.
All right, let's move on to the chassis or drivetrain of your robot. How is it developed? What type of motors are you using? Odometry, stuff like that.
We are currently using 435s, Yellow Jackets, and Go Build a Grip Force Mecanum wheels. We found that these strafe a whole lot better than the old Go Build wheels. So it's been a great thing this year. With our low center of mass, this has really increased everything to the point of we can be traveling across the field at the fastest rate.
Also on our drivetrain, we have our odometry. This year we switched to optical odometry, which is really, really nice. We get basically no error with it, but with the three-wheel odometry, the normal stuff that most people use, it does occasionally slip and occasionally gets off.
So what was the main reason behind switching from three-wheel odometry to optical? And what are the type of improvements that you've seen by switching?
So like I said before, the optical odometry sensor, it has a lot more, it has a lot less error. For example, we can drive 3 times around the submersible and we got, was an inch of error just on the coordinates of the robot. On the heading of the robot, it is not perfect, but after spinning around 5 times, we got a error of 5 degrees. And because it's using an IMU to track its rotation, and it's using this lens to track where it is on the field.
Yeah, that sounds incredible. The optical odometry that I've seen this season has definitely been an improvement over your normal 3-wheel or 2-wheel odometry. Moving on, let's talk about your active intake, which was pretty stellar today. It worked most of the time from what I could see. It was pretty efficient, so let's talk more about that.
This is our extendable intake this year. As soon as we saw the game, we wanted a touch-it-own-it style intake, and we're able to achieve this by having a top-down roller intake with a pass-through. Okay, as you can see, we have a color sensor inside of our intake, and this means that we can stop the samples inside of our intake. Additionally, if the sample is the wrong color, then we can simply pass the sample through the intake. Like that. This means that even if we never have to outtake our intake, even while searching through the submersible.
Yeah, moving on next, let's talk about your outtake system, which is a claw that grabs from the active intake. How did you guys develop that? What sort of thought process went towards it, and how did you make it work?
So one of the best ways we made it work was that we decided to put our claw at a 45-degree angle so that we can drive directly up to the sub and clip them on instantly, so that we can just slam directly into the sub and don't even have to think about it. Driver's just done the second they get there. We're also actually don't have a way to transfer specimens, but we don't need it. We have a way to grab off the back with the same arm so that we can intake the samples off the ground and specimens off the wall, so that we can keep them separate and not have to worry about intaking something.
Yeah, that's all incredible. Your outtake was amazing today, and your autons every single run, you're always getting at least 3-4 specimens on the high chambers. So really interesting to see. Moving on, let's talk about your level 3 hang, which is one of the most unique hangs that I've seen so far this season. Let's talk more about that.
All right, to start off our level 3 hang, we have a powered takeoff system. in our drive base here, which is on a Studica linear servo that actuates a gear to shove into the drivetrain and makes it so that we can drive around and then put all of these together. We have these stilts that can come out with the drivetrain with a constant force spring on here. Alan, just move it up, please. Yep, there we go. So this gets our first level. We hang on to here and go down. Obviously, we move our arm out of the way. But after that, we have these hooks deploy out the top. And then once we're up there, we can grab the level 3 bar and get that. Yeah. I don't know. But we're able to do this because we made these stilts at the right length so that we can brace on that bottom bar and not touch the ground. So this has allowed us to get a really convenient center of mass to the point of we don't even have to think about the center of mass and when it comes to calculating how and what we needed to do for this climb.
Yeah, so the one thing that I'm really interested in is why did you decide to use constant force springs for the initial stage of your hang as opposed to any other solution like servos or a motor?
Yeah, so the main reason we use constant force springs is because at our first competition, we noticed that our climb wasn't as fast as we really wanted it to be. So constant force springs helps a lot. We actually are using ThriftyBot constant force springs, which are able to, which currently have about 14 pounds pulling the robot up. And we were originally going to go with larger ones to get about 20 pounds, but they were a little bit too large for our system.
Yeah, and then finally moving on, let's talk about your software. Obviously, a robot like this has many complex mechanisms, so the software is, of course, going to be very complex as well. How did you navigate writing your code and making sure that everything worked together well?
All right, so on the software, so this year we have a lot of complex stuff. Like, for example, if we wanted to transfer, we have to bring this down into the robot, grab, and then bring it up and then out of the robot. So to do that, I have a subsystem in my code that's purely, or a complete file that's completely just for the state machine. And so basically, if we grab a piece here, if we grab a piece, it then goes into the tray, as you can see, and then we can hit this button to transfer it, and basically it spits it out into there, grabs it, and then comes back up. And then we can also then place off the back up here. And then also, whenever we drop into the tray, our robot knows that it needs, the next thing we're going to do is grab again out of the submersible. So basically, it can just come to place and then come down into the store position. So it's already ready for the next time. Also, with the state machine, we can basically press one button and do the entire robot subsystem. So if we grab another one here, and then this time, all I'm going to do is just press one button, which is this one. It can automatically do everything itself. So this way, our drivers don't have to worry about hitting the right buttons multiple times or anything like that. We have presets for literally everything.
Yeah, and then lastly, do you use how are you tracking all of these positions? Are you using any sort of PID loops, encoders? Are you using like Axon that has like their analog encoders?
All right, so to keep the position of our lift, we're just using the encoder out of the motor. For these slides, we have just the encoder in the motor. And then to track the state of the robot, we have 3 variables in code that we figured out are the only 3 variables that we'll need. And it is, does it have it in the intake? Does it have it in the outtake mechanism? And are we at the store position, which is this position right here? So basically, if we're at store position and we want to go up here, we have to first raise up the slides and then go back. But if we're not at store position, then we can just go straight back.
Something that we made sure to implement this time around is we put limit switches on every set of slides, and we used the detections in code on when to stop anything that goes linearly that has something that may slip. We're currently using belts on these guys, so slipping is a thing that can happen, but with the code that's able to track how much current we pull through amperage or current amps.
Well, it's current and the current unit that we use in amps.
Yeah, so we're able to track everything whenever it is, and we have the power to reset that without disabling towing up. The arm is done by the internal PID on our AGFRC servos for our arm. We find that they're a great alternative to axons, and occasionally axon we can't get from them, so we've resorted to these. So
Also, another thing that uses current on a robot is our intake mechanism. We wanted this to basically, if it jams, we want it to automatically just spit it out and just basically be able to do anything. Basically, if it, yeah, show that very well, but don't put it in. Basically, if we were to jam, you can see it spinning this way. If we were to jam it, it automatically outtakes my hand. So it basically will spit it out if it's jammed, or if not, then it'll just keep intaking it until it grabs it. All right.
And then you also have a limelight on the front of your robot. Could you explain what you're using the limelight for this season, especially since there isn't any like randomized task?
So the only randomized part of the field is actually the submersible, and currently we have a 5 specimen auto, which is quite consistent, especially when we're not on the playing field. So we're really hoping to implement a 6 specimen auto in the future, and with samples, we can get all 4 samples that are preset in about 16 seconds at our best. And so we're hoping to get a lot more samples in the future. So we want to talk about a little bit about how the limelight works. I have 3 different pipelines set to threshold out the color values outside a set RGB range. Then at areas of high density, where the blocks are most likely to be, it will draw a bounding box around them and then find the center of that. Based on that point and the angled offset from the center of the block, we are able to use trigonometry to calculate the real world position relative to our robot. And then, do you want to talk about?
Yes. So then, given all the 3D positions of the blocks relative to the robot, we are able to check how much time it'll take us to collect each block, and then we can basically use this to see which block is the best choice to pick. And we do this with a system of parametric equations. We can do this both for polar coordinates and both for Cartesian coordinates, which is very helpful.
Right, and then the last thing before I go, their intake CAD is actually publicly available online. So please make sure to check the description if you want to see how their intake works or even use it on your own robot. So anyways, thanks for joining me on Behind the Bot, and I'll see you viewers next time.